Pick 6 and 8 from the homework sheet to go over. I think these two will give most of the main ideas that I want to make sure you get to see here. So on number 6, we'll start with amplitude. That's kind of the easy part. Remember, amplitude is distance, if you think about a wave, distance from the middle, so distance is always positive. Even though this is a -2, amplitude is +2. When we go to graph, the negative will matter. Okay, so it does play a role, but for amplitude, it's just +2. Before I get to period, it's probably good to do frequency. In this case, it's going to be 3. It's just the number beside x. But you got to remember that the normal period, the normal time to do one cycle of tangent is pi radians. That's all it takes. -pi/2, +pi/2. I just realized I'm talking about cotangent here. So 0 to pi for cotangent. Both of those, tangent and cotangent, pi radians to do one full cycle. And then it starts over. It doesn't look like a wave, but it's between the asymptotes. Think about it that way. So the period, it only takes pi radians to do one cycle, but we're going to get 3 full cycles in that normal time period, so we're dividing that by 3, divided by frequency. And then finally, phase shift. Before I do this part, I like to kind of sketch what the cotangent normally looks like, so I've got something to compare to, and this will help with the graph later anyway. So just a little tiny sketch. It's not really part of the problem, just up there for me to kind of reference. So cotangent, that will have an asymptote at 0 and another asymptote at pi. So 0 and pi. And the normal cotangent halfway in between pi/2 is at 0. And it kind of comes down like that. Now, another big reason I like to do that is when I do the starting and ending point for a normal cycle, I've got a good idea of what to set this stuff equal to. You can set this equal to any piece of the cycle there, but it just makes sense to do it to the asymptote, so you've kind of got that starting and ending part of a cycle. So I'm going to take the 3x minus pi/4, and I'm going to set it equal to 0 because that's where the cycle would start normally. So I want to see, what do I have to plug in here for this whole value to be the same as where it would normally start at cotangent of 0. So 3x equals pi/4, that means x is going to equal pi/12, and I divide by 3. So that is my phase shift. So this thing will be scoot over pi/12. That's another reason I picked this example, because the phase shift is kind of weird. You've got to really be careful labeling the axis here. All right, so that's also going to be what I'm going to label as my start, because I also want to think about the ending for one cycle again. So normally I'd be putting pi in, I'd be taking cotangent of pi to end a cycle. So I want to see where this stuff equals pi. So 3x minus pi/4 equals pi. This will show me where the one cycle would end if it started here. So 3x, let's see, we had pi to pi/4, so we need to make that into fourths. So that'd be 4 pi/4, so 5 pi/4. X will be 5 pi over 12. Okay, so this will end at 5 pi/12, start at pi/12. So let's move into the graphing part. Now I'm going to ask you to do 2 full cycles on your assessments, so let's make room for that. So pi/12 is where I'll start, and I'm going to go ahead and put 5 pi/12 kind of in the middle. And if you kind of see where the trend's going, you can use your period to figure this out. Let's just check and see if this makes sense while we're at it, because this distance here has got to be the same as the period, or we've done something wrong. So from pi/12 to 5 pi/12, that's 4 pi/12 radians. 4 pi/12 is pi/3, so that's looking good. Since we're in 12ths, I would just add 4 pi/12 to this. So 9 pi/12, that's where the next cycle will end. Halfway in between here, we're in 12ths, so 3 pi/12. That's probably not the best way to leave that though. 3 over 12 is 1/4, so pi/4. And then halfway in between those, that was 3 pi/12. This would be 2 pi/12. 2 over 12 is 1/6. So let's see, so 1 pi/12, 2, 3, 4 pi/12 would be pi over 3 there. It's okay if you need to write those out in like 1 over 12, 2 over 12, 3 over 12, and so on, and then reduce, that's fine. But just make sure you do put them in their most reduced form on your final answer. That's important. You really need to have this stuff reduced. All right, so keep count by 12s again. Halfway in between be 7 pi over 12, which we can't reduce that one, thankfully. 6 pi over 12 would be pi over 2, and 8 pi over 12 would be 2 pi over 3. Okay, so reduce all those fractions, make sure it looks good. And I just realized I probably shouldn't leave that as 9 pi over 12, because that is 3 pi over 4. All right, I think everything's reduced now. We should be good to go. Let's start putting the asymptotes in here. All right, the reason I do this starting and ending point, and I've got my reference up here to think about. Cotangent is going to start with an asymptote and end with an asymptote at this starting and ending point. So at pi over 12, and then again at 5 pi over 12. While we're at it, again at 3 pi over 4, which is 9 pi over 12. Those are my asymptotes. So cotangent would normally come down, hit the axis right in the middle, and then continue on. And that would be the cycle. But this one had a -2 out front. So everything that was positive becomes negative, everything that was negative becomes positive. It flips that around. So when I go to graph, what I typically do is just kind of just a loose labeling where I make sure I hit the amplitude on there. Maybe put enough tick marks so it's pretty obvious. But as long as you've got that -2 on here, that's really all you have to have. Now, halfway in between the asymptotes, it will be at 0. So we're good with those. All right, remember, cotangent again would come down, but that -2 out front is going to flip things around. So had it been just a 2 out front, at pi over 6 we'd be up at 2, but we're going to be down at -2. And at pi over 3 we would have been down here, but we're going to be up at 2. So it flips it around. And just make sure you don't touch your asymptote. Make sure you got arrows on the end. And then let's do one more cycle. So -2, or at pi over 2 it's -2. At 2 pi over 3 it's a +2. And again, just make sure you got the curve to it. Make sure it doesn't touch the asymptotes. Make sure it goes through those points. And that should do it. I'm going to go back to Desmos and just check. Let's just keep in mind a couple of these key things. Pi over 12, 5 pi over 12 are asymptotes. Pi over 4 is where it crosses the axis, so let's see if those are showing up. Now, just to point out what I'm doing here, this is the Desmos I made for you all. Came down to the other functions folder, did the cotangent function, and you can look where A, B, and C are in that function. I just put them in there from what we started with here. We've got -2 for A, 3 for B, -pi over 4 for C. So -2, 3, -pi over 4. C, be really careful, make sure that you do put minus there if the term's negative. Another thing I did, I added in these asymptotes. So you can pick any blank line over here you want, just type whatever you want in there. Asymptotes are vertical lines, so they do need equations. They're x equals equations, so make sure you do that part. But I put in x equals pi over 12 and 5 pi over 12, and let me do projector mode so it shows up a little better. But hopefully you can kind of see that. If you zoomed out, you could definitely see that. Those are the asymptotes. They're looking pretty good. It's not touching those. And at pi over 4, 0, that was the point right in the middle. If you want to check another one, 7 pi over 12, 0 was another place where it was in the middle. So we'll come down and just check, make sure that checks out, and it seems to. So you can check as many points as you want. You could also type in x equals pi over 3 if you wanted, and you should be getting 2. I'm not going to do it. The way that would look is it would put a vertical line right here, and then you can see where they intersect, and you can confirm it that way. Number 8, another one where it's a negative out front. So the amplitude here is just +1. Again, amplitude is always positive. It's the distance from the median, from the middle of the wave, or the trig function. All right, period. Well, frequency in this case is 1/2. Let me go ahead and put that in there. You don't have to do that. I just kind of think it's helpful to put that in because the normal period divided by frequency is how you get the period for the function you're looking at. So think about it this way. The waves are going to develop half as quickly, so they're going to be wider. So normally cosecant, that comes from, or it always comes from this sine function. Sine function from 0 to 2 pi is 1 cycle, so 2 pi radians is 1 normal period, 1 full cycle. We're going to divide that by half, so we're going to get 4 pi radians. Okay. Now, phase shift. I'm going to do that same thing again. I'll do a little quick sketch. Cosecant comes from the sine function. So sine goes to pi over 2, pi kind of in the middle. Now instead of actually drawing it in, I'm just going to kind of dot the sine function because we're doing cosecant, we're not actually doing sine. And I'm just going to do the normal sine function. Okay. So let me just make a note here. This is cosecant. So the normal sine function, up to 1, down to 0, -1, back to 2 pi. But if I'm going to do cosecant, then everywhere the sine was 0, we've got an asymptote. Because really that's 1 divided by sine. That's what cosecant is. And everywhere sine was 0, that's 1 divided by 0, so that's technically infinity, so it's an asymptote. And then it's these little U-shapes in between. They're not parabolas, even if they kind of look like it, they're truly not. You'll see the properties of parabolas in chapter 9, I think it is, later. And these are not quite parabolas. So, phase shift. Let's see. Well, we want to compare it to where sine typically starts and where sine typically ends. So for phase shift, I really just need to compare it to where sine normally starts, or cosecant. Either way, they're really the same, from the same function. So x over 2 minus pi over 2 equals 0. X over 2 is pi over 2, and if I multiply by 2, I get pi. So my phase shift is pi here. All right, that's my start. And I want to see where I'm going to end. This is just really to do the graph. So normally when you were taking cosecant of 2 pi, you would be completing the cycle. So I want to take this stuff in here, and I want to set it equal to 2 pi, because that's where I would normally end. So x over 2, let's see, it'd be 2 pi plus pi over 2 when I do that to both sides. That'd be 4 pi over 2 if we convert it. So 5 pi over 2. Multiply by 2, x is going to be 5 pi. Now, let's check the distance between pi and 5 pi. That's 4 pi, so that should be the period, and it is, so we're looking good there. All right, so use the beginning and ending as kind of a guideline of how to set up your graph. Pi, 5 pi, so pi radians is in the beginning, 5 pi is kind of in the middle, because I want to show 2 full sections. And if I get 4 more, that's 9 pi. This one won't be as bad to label all the terms. 3 pi is in the middle, then 2 pi here, 4 pi, 6 pi. Really just count my pi's. Okay. And really I'm just taking this, dividing it in 2, and then dividing those in halves to get the quarters. I mean, that's all these functions. If you divide them into 4 sections, that's always the way to go. All right, the key points. Well, it's going to begin with, actually, I'm going to graph a sine function first. A sine function that begins with pi, and we know halfway between it's back to 0. When it ends the cycle with 5 pi, it's back to 0. Start another cycle. You don't have to do it that way, but I'm just going to put them in there. All right, now normally sine is going to go up. Let's pay attention to our a value up front. It's -1. So sine typically is going to go up to 1 first, but this has been flipped, so it's going to go to -1, back to 0. And again, normally sine goes down after the middle point, but this is flipped, so it's going to go up. So it's just kind of the opposite of a sine wave. It's sort of flipped over. You know what, before I do all that, let's just make that dotted, because that's really not our final function right there. This is just kind of a guideline. All right, so there's the outline of a sine function, because really I'm graphing cosecant here. So everywhere that sine was 0, I'm going to put some asymptotes in there. And then we're just going to come back everywhere that it's has a minimum or maximum, put those little U-shaped drawings in. And that should do it. You can go back to Desmos and check. But that's good enough for 2 cycles. That'll do it.